Welcome back. Today we're diving into fault tolerance. This is the key to achieving the high availability we discussed last time. Here's the fundamental truth: things will break. Hardware fails, networks get congested, software has bugs. You cannot build a system that never fails. It's impossible. So what can you do? Build a system that can tolerate failures. That's the essence of fault tolerance, continuing to operate even when parts fail. Maybe at reduced capacity, but the system keeps running. Let's use an analogy. Think about your car. A car has 4 tires essential for operation. If one tire goes flat, the car can't drive normally. But most cars have a spare tire in the trunk. The spare is a redundant component ready to swap in when needed. It doesn't prevent the flat, but it lets you continue your mission. How do we build these spare tires into our systems? It comes down to 3 core ideas. Redundancy, having more than one of critical components. Replication, keeping multiple copies of your data. And failure detection, knowing when something has failed. Let's start with active-passive redundancy, also called failover. You have at least 2 identical components. One is active, handling all the traffic and doing the work. The other is passive, a hot standby, running but not taking traffic. A monitoring system watches the active component. If it detects failure, traffic is rerouted to the passive server. From the user's perspective, there's maybe a tiny blip, then recovery. This diagram shows the failover process as a state machine. Normal operation continues until the primary fails a health check. The system detects the failure and triggers failover. The standby becomes the new active server. The system recovers automatically without human intervention. This is much better than a full-blown outage. Now let's look at active-active redundancy. All components are online and actively handling traffic. A load balancer distributes traffic among all servers. If one server fails, the load balancer stops sending it traffic. The remaining servers absorb the extra load. No idle resources, you're using everything all the time. Let's compare these 2 approaches side by side. Active-passive is simpler but has idle resources. Active-active uses all resources but is more complex. Active-active has faster recovery, no failover event needed. The trade-off is ensuring your app can run on multiple servers. Choose based on your specific requirements and complexity tolerance. Now let's talk about replication, redundancy for data. You don't want just one copy of your database. If that server's hard drive fails, you could lose everything. So you replicate, keep identical copies on multiple machines. There are 2 main modes, synchronous and asynchronous. In synchronous replication, the database waits for all replicas. When you write data, it's sent to all replicas first. The database waits for every replica to confirm success. Only then does it tell your application the write succeeded. This is incredibly safe. Data is guaranteed on multiple machines. The downside? It's slow. Latency depends on your slowest replica. Look at all those steps the client has to wait for. Now compare that to asynchronous replication. The primary saves data and immediately confirms to your app. Then it sends the data to replicas in the background. This is much faster from the application's perspective. But there's a catch: replication lag. If the primary fails during that lag, unsynced data is lost. So which do you choose? It's a classic trade-off. Synchronous gives stronger consistency and durability. Asynchronous gives lower latency and higher performance. For financial transactions, you'd probably choose synchronous. For social media likes or view counts, async is often good enough. Make this decision consciously based on your requirements. Now for the missing piece, failure detection. How do we know when something has failed? A failover system is useless if it doesn't know failure occurred. The most common mechanism is called a heartbeat. Each service regularly sends an "I'm alive" message. This state diagram shows how heartbeat monitoring works. A server starts in the healthy state. As long as heartbeats arrive, it stays healthy. If a heartbeat is missed, it moves to suspected state. This avoids false alarms from temporary network blips. If timeout exceeds, it's marked failed and recovery triggers. Here's a practical health check endpoint in Python. We create a simple Flask app with one endpoint/health. When called, it checks if the database connection works. If all checks pass, it returns HTTP 200 OK. If a dependency is down, it returns HTTP 503 service unavailable. A load balancer sees that 503 and stops sending traffic. This is a fundamental building block of fault-tolerant systems. The health check doesn't do business logic, just reports status. Monitoring systems call this endpoint every few seconds. Automated detection leads to automated recovery. Now let's talk about transient failures. These are temporary glitches, network drops, brief overloads. If our code fails on the first try, we shouldn't just give up. The problem might fix itself in a few hundred milliseconds. The solution is to implement a retry mechanism. But we have to be smart about retries. Immediate retries can cause a retry storm, making things worse. The smart approach is exponential backoff with jitter. First retry waits 100 milliseconds, second waits 200 milliseconds, third waits 400 milliseconds. You double the wait time with each failure. Jitter adds randomness so clients don't all retry at once. Here's Python code implementing exponential backoff. We create a decorator that wraps any function with retry logic. Inside a while loop, we try to execute the function. If it succeeds, we return the result immediately. If it throws an exception, we catch it and wait. Then we double the delay and add some random jitter. The loop continues until success or max retries reached. This is incredibly powerful for building resilient clients. It handles temporary failures in services you depend on. Apply this pattern to any external service calls. Now let's zoom out to microservices with the circuit breaker. When you have dozens of services talking to each other, the chance of any one failing at any time is quite high. If one failure cascades and takes down everything, you have a problem. The circuit breaker pattern prevents this cascade. Think about your home's electrical circuit breaker. If an appliance draws too much current, the breaker trips. It cuts off electricity to protect the rest of your house. The software circuit breaker works exactly the same way. It has three states: closed, open, and half open. When closed, traffic flows normally through the circuit. The breaker tracks how many calls are failing. If failures cross a threshold, the circuit trips to open. Now it doesn't even try to call the failing service. Requests are immediately rejected. This is called failing fast. This gives the struggling service breathing room to recover. After a timeout, it moves to half-open state. It allows one test request through to check if service recovered. If the test succeeds, circuit closes. If it fails, back to open. Here's the circuit breaker protecting services in action. The shipping service calls address service through a circuit breaker. When address service times out, the circuit tracks the failure. After enough failures, the circuit opens. New requests fail fast without even trying the broken service. This prevents localized failures from causing system-wide outages. Critical for building stable microservice architectures. Let's summarize the key takeaways from today. First, failures are not exceptions, they are the norm. Design from day one assuming components will fail. Second, redundancy is your primary tool against failure. Use active-passive or active-active for services. Use sync or async replication for your data. Third, automate failure detection and recovery. Use health checks, heartbeats, retries, and circuit breakers. Next time, we'll explore scalability. See you then.